Hey everyone, and welcome to the final lecture or the final video on the S-block elements and their compounds. And this time, just to round it off, we're going to be looking again at the exceptions. So we saw that lithium and beryllium behaved quite differently to the rest of the metals in their group. So we're just going to summarize these exceptions, how they behave differently, have a brief look at why they behave differently, although we've touched upon it in the videos before, and then just a summary of what we've looked at. So I've got some diagrams of all the reactions of these compounds and how they link to each other, just to try and summarize it all in one place. So we'll start by looking at the group 1 exception, which is lithium, and summarizing its exceptional behavior. So lithium will burn in air to form lithium oxide as Li2O with the oxide anion, so O2 minus. Whereas all the other group 1 metals, if we burn them in air, they either form peroxides, which have the O2 2 minus anion, or superoxides, which are O2 minus. Lithium hydroxide also behaves much differently. So all the other group 1 hydroxides, if you heat them, are generally stable, they're thermally stable. Whereas if we heat lithium hydroxide, that decomposes to give us lithium oxide. And finally, a lot of the lithium compounds are far less soluble in water than those for the other group 1 metals. So what's the reason for this? Well, it actually fits what we expect, and it's because lithium, or the Li plus cation, is so small and has a very high charge density. So it's very polarizing, and this means there's a lot more covalent character to the lithium bonds than with the other group 1 metals. And this leads directly to changes in things like the lattice enthalpy and the Gibbs energies of hydration. And these, in turn, affect thermal stability and solubility, like we've seen in the previous videos. Now, if we look at group 2's exception, beryllium, I think it's even more exceptional than lithium. Like, it behaves a lot differently to the group 2 metals. So beryllium as a metal doesn't react with water, whereas all the other group 2 metals do. It's amphoteric, which is a big difference. So like, it behaves as an acid and base. It can react with acids and bases, whereas all the rest of the group 2 metals are basic. They only react with acids. Point 3 is actually more of like the reason behind it. It has more covalent character, which we'll see in a second. And the beryllium oxide doesn't react with water, which is again in contrast to all the other group 2 oxides. And much like with lithium, this fits the expected pattern, and then some more. So beryllium is again a small cation, and it's got high charge density, and this is even more so than with lithium. So it's still small, but where it's 2 plus rather than 1 plus, it's got an even higher charge density. It's even more strongly polarizing, and this means there's a really big or high degree of covalent character to the bonds that the beryllium cation forms. And again, this leads directly to changes in the lattice enthalpies, Gibbs energy changes of hydration, and therefore thermal stabilities and solubilities. And this slide shows how we've got more covalent nature, and what I'm using it importantly for is to show polarizability in a graphic form, which I haven't done yet. So first, if we look at the electronegativity, so we've seen this electronegativity periodic table a few times, you can see that lithium is much higher than the rest of group 2. Therefore it will make more covalent bonds. And if you look back at the triangle we were using to predict the ionic covalent nature of bonds in lecture 2, you'll see that again with lithium, but not such an extent, is still got quite a low electronegativity. But the real thing was the polarizability that we were talking about. So they're very small cations because they're at the very top. And they're in the 2s shell, so it's a very small cation, and very small cations are very polarizing. And there's a graphic here. It's because there's a lot of charge in a small place, so it can distort the electron cloud of something else. So on the left hand side, we're showing how size and charge, and therefore charge density, has an effect. So sodium 1 plus, which is a much larger cation than lithium or beryllium, has distorts the anion, so in this case chlorine, but it could be any anion, the electron cloud a little bit, it pulls it towards itself. But as we get smaller cations and or more charge, so that's why beryllium has a really covalent character. It's a very small area with a very high positive charge. It distorts the electron cloud of any anion, and then you see they sort of almost overlap, and it becomes much more covalent, like the electrons are between the two atoms, like in a covalent bond, rather than this example here, say, where they're point charges. They're much more ionic interactions. So this covalent nature is why beryllium and lithium are very different. And if you want to read more about polarizability, where I took this figure from, is this link down here, and that explains quite well the nature of polarizability and how large anions and small cations are more polarizing and more polarizable. So finally, I said I'd summarize the first 6 lectures, I guess it is, all the reactions in a couple of slides. So I've got one slide for group 1, which is this one, and then the next slide for group 2. So I think if you need it as a reference, hopefully it's helpful, but I'll run through it quickly. So group 1 metals are very reactive with water and oxygen. That's why they're stored under oil. So all of them react with water to make a hydroxide, and react with air, or the oxygen in the air, to form an oxide. Which oxide it is depends on what the metal is, as we've seen. All these oxides will also react with water to give the hydroxide. And as we've seen, these hydroxides are thermally stable, except for lithium, which if you heat it will turn back into the oxide. The hydroxide, we can react with a suitable halogen acid, so HCl, HF, HBr, whichever you want, to make the metal halide. And then finally, looking at the carbonates, which was the last video, you can also react the carbonates with the halogen acid to make the halide. Lithium carbonate, the only carbonate, will decompose upon heating to form the oxide. And then with the nitrates, that all will thermally decompose, but lithium will decompose to the oxide, and all the rest will decompose to the nitrite. And then I've got a similar reaction summary for group 2. So all of the metals are again quite reactive, but not as reactive as group 1. They all react with oxygen to make an oxide. There's much less choice here. Most of them will make an MO style oxide. As you go down the group, things like barium are more likely to make the peroxide. Reacting with water, we've seen that beryllium is an exception, but the rest of them will form the hydroxide upon reaction with water. Again, the oxides will dissolve in water, again with the exception of beryllium, to make the hydroxide again, also. And these hydroxides, if you heat them, this time they'll all decompose thermally to give the oxide. Now we've seen that these routes we can't use with beryllium to get the hydroxide. So if you want beryllium hydroxide, you've got to react the beryllium halide with OH minus anions, so like in a base, with a base, to form the hydroxide that way. We form the halides by reacting the metal directly this time with a halogen gas, so whichever halogen you want in a gas form, to form the halide. And then this time it's much simpler with the oxoanions. They all decompose upon heating to form the oxide, and whichever suitable gas will come off as well. So that's it for the S block. We have finally reached the end, and here are a few more questions to test your knowledge. So 2C and 4, which I took out of last time's questions because they involved some of the oxoanions. 6, 7, 14 and 18, and I'll make a worked example video of these again very soon.